Hi there. In this equation we will solve exponential and logarithmic equations. First of all, an exponential equation is an equation where the variable is in the exponent. In this particular case, b to the x equals p, the variable x has been exponentiated with the base of b. In other words, the exponent has been put on a base of b. We call this exponentiation base b. Now to solve or isolate for the exponent x, we have to undo that operation by applying the inverse of exponentiation base b, which is logarithmication base b. So to our given exponential equation, we apply log base b to both sides of the equation, and then log base b of b to the x, if we remember by the inverse property, log base b of b to the x, log base b and b to the cancel, leaving us with just x, and then we apply log base b to the other side. So we can apply the change of base formula for the logarithm laws to rewrite log base b of p using any log base, or in this case, base e, to give us ln of p divided by ln of b. So we will use logarithms to solve only if the power p cannot be expressed as a perfect power of the base. So for example, if we have the powers of 2, 4, 8, 16, 32, and we happen to have any of these numbers as the power on the other side when the base is 2, logarithms won't be necessary because we can just get common base of 2 on both sides and use the one-to-one property. There is no restriction on the values that an exponent can be. It can be any positive, negative, zero, fraction, irrational, whole number that we like. But we should in general check the domain of any function or expression when we are solving equations or inequalities. So let's take a look at an example. In number 1a, we have a simple exponential equation. By simple, I mean that we have one term on each side, we have one base, one exponent, and one power. And we recognize that the power of 8 is actually a perfect power of 2, and so we can use the one-to-one property. We have the power on the left equals the power on the right. Their bases are the same, and therefore by the one-to-one property, the exponents must be equal. So we get x is equal to 3. Now, in the next question, we see that 9 is not one of those perfect powers of 2. Again, if we wrote them, we would get 2, 4, 8, 16, 32, 64, and so on. If you're not familiar with the perfect powers of 2, I recommend that you go back to the table of values and make sure you know all the perfect squares, perfect cubes, and perfect powers of base 2, 3, 4, 5, and 6 that are given in the table. Now, I left a little gap here because 9 is a power, and 9 lands between the perfect powers of 2 that are 8 and 16. In particular, we know that 8 is 2 cubed, and we know that 16 is 2 to the 4. And so we would expect the exponent that we put on base 2 to get 9 lies somewhere between the exponents of 3 and 4. But because we cannot write 9 as a perfect power of 2, we can apply log base 2 to both sides of this equation to undo the 2 to the and isolate x. So we apply log base 2 to both sides of the equation. We get log base 2 of 2 to the x equals log base 2 of 9. Now another way to write 2 to the would be to use the caret notation. And it's a little bit easier in this case than for us to recognize that log base 2 and 2 to the cancel, leaving us with x. But of course that was the whole reason for applying this inverse to undo the 2 to the in the first place. So you could see that happening, and then the x lands on the ground level as opposed to up in midair. So we get x is equal to log base 2 of 9. Now this is not really a surprise, because when we think back to what this means, this notation is shorthand for the exponent that we put on base 2. I'll just write it out, to get the power of 9. And I'll just put which yields or to get the power of 9 for shorthand. And so we were really looking for the exponent that we put on base 2 to get the power of 9. So all of this is the answer, the exponent that we put on base 2 to get the power of 9. And all of that is just shorthand by writing log base 2 of 9. So we're done. That's it. Now if you wanted to approximate this, we'd have to go back to these sequence of numbers. Now I'm just going to make this a little bit bigger for a moment. And we can see that there's an exponent that we would have to put on base 2 to get 9. Namely, that exponent is log base 2 of 9. So 2 to the log base 2 of 9 This isn't a surprise because the 2 to the and the log base 2 cancel, so 9 is equal to 9. And furthermore, we see that the exponent that we put on base 2 to get 9 lies between the exponent that we put on base 2 to get 8 and the exponent that we put on base 2 to get 16. In other words, log base 2 of 9 lies between the perfect exponents, or the whole number exponents, of 3 and 4. And so we can see that log base 2 of 9 is 3 point something. Let's just take a look on a calculator to confirm. So if we work it out, just using the log button, we get log base 2 of 9, and to approximate it we see 3.16993. In other words, 2 raised to that exponent is 9. Now we'll notice here that it says actually 9.00006 because this decimal that we used was an approximation. So we want to really think, what's a better way to write the exponent that we would put on 2 to get 9? And the exact answer, of course, is log base 2 of 9. So if we want to know the exact expression, we call it log base 2 of 9. And if we want to approximate it, we can use our calculator to 1, 2, 3, or more decimal places. And here the 2 to the and the log base 2 cancel, and we're left with 9. Okay, let's take a look at part C. Very similar question. Don't let the fraction or the fact that there's a 2 on the other side throw you off. This is 4.5, which is not a perfect power of 2. So again, to this equation, we apply log base 2 because we want to undo exponentiation base 2. And we end up getting log base 2 of 2 to the cancel, so we have x on the left, and we get log base 2 of 9 halves on the right. And we know that 4.5, which is 9 halves, lands between 4 and 8, these powers. And 4 is 2 squared, so this exponent of log base 2 of 9 halves would land between 2 and 3. We can go back to our calculator and we can approximate that value. So that's not the expression I want. I'll just start again. Log base 2 of 9 halves is somewhere between 2 and 3, 2.16993. And so that makes sense from what we expected. Now there's another approach to this, and that approach is simply by recognizing base to the exponent of x equals the power p is equivalent to log base b of p equals x. So if I wanted to isolate x, the exponent, I would simply need to convert exponential form into log form. So I'm going to rewrite my exponential equation here. I'll do it in green. 2 to the x equals 9 is equivalent to the rearranged logarithmic form, which still conveys the same information of base, power, and exponent. So we would get log base of the same base, which is 2, taken of the power, which is 9, and that will equal the exponent, which is x. And so in one step, we've rearranged and we're done. Doing this one-step conversion is kind of like when you were in Algebra 1 and you used to have something like 5x equal to 15. At the time, you needed to show the steps of dividing by 5 and then get x equal to 3. But now, you're so familiar with this undoing step of division that you go immediately from 5x equals 15 to x equals 3. So this one step here is like the one-step conversion from exponential to logarithmic form, or vice versa. Showing the step of applying log base 2 is like showing the step of dividing by 5 was back in Algebra 1. Okay, in the next question, we want to get equal powers with like bases. So again, you need to recognize the 3 and the 81 falling in the same sequence. So the sequence of powers of 3, we have 3, 9, 27, 81, 243, and so on. Without recognizing these numbers, solving these by hand is very difficult. So I'm going to get a base of 3 on both sides. And the first thing I notice is that 1 over 3 is 3 to the exponent of negative 1. Do make a habit of saying 3 to the exponent of negative 1 and not 3 to the power. And then we have x squared plus 4 as the outer exponent. And we can rewrite 81 as 3 to the 4. So then by our exponent laws, we can keep the base and multiply the exponents, which gives negative x squared minus 4. And then on the right side, we keep the base and multiply the exponents to get 4x. Because we have a single base on the left equal to, rather, a single power on the left equal to a single power on the right, and the bases are the same, by the one-to-one property, we can conclude that the exponents are equal. So we end up having a quadratic equation, and I'm going to take all the terms to the right side by adding x squared and 4. So we get x squared plus 4x plus 4, and all of that is equal to 0. So we might want to rearrange it so that the variable, well, the non-zero side is on the left. And then we can factor this, which ends up giving us x plus 2 all squared equal to 0. And then we see that x is equal to negative 2. So we have one solution here, and we can substitute the values for x in to confirm that the left side and the right side are equal. You might want to pause the video at this point and just try the next question on your own. But to do that, we need to get first a simple exponential form. And by that I mean a single base to an exponent equals a power. So one strategy you might find useful is to take the part or the term or the piece of the equation that involves a variable and let that be some completely different variable, like a. So if I were to let a equal 1/2 to the exponent of x over 3, and then rewriting the equation, I get 20a plus 8 equal to 13. This is a linear equation in a because a is raised to the exponent of 1, and I can easily solve this equation for a. So a is equal to 1/4, and then I back substitute and replace a with the original expression in terms of x. So I have that x is equal, or rather that a is equal to 1/2 to the exponent of x over 3, and that's equal to 1/4. Now I want to get a like base on both sides, and I can either say that the base on the left and the right is a half, or I could see that the base could be written as 2. I'll write it as 2, and so 1/2 is 2 to the negative 1, and then 4 is 2 to the negative 2. So we can rewrite this by expanding the exponents. And then, because we have a single power on the left equals a single power on the right, and those powers have the same bases, then by the one-to-one property, the exponents must be equal. And we can solve this equation by multiplying both sides of the equation by negative 3. Negative and 3 will get rid of the negatives divided by 3. And so we end up getting x equals positive 6. So you can substitute that value in and make sure that we have the right answer. Let's just do it mentally quickly. Well, in fact, I'll just put a quick working out here. So we're going to get 20 multiplied by 1/2 raised to the exponent of 6 divided by 3, which is 2, and then plus 8, and we're questioning if that's indeed equal to 13. A half squared is 1/4 because it's a half times a half, and a quarter of 20 is 5. Lastly, 5 plus 8 indeed equals 13. The next question gives us a hint or a clue to use the method of substitution. In fact, we already used the method of substitution in the last equation. However, it's a good idea to use a method of substitution if you ever see an expression, a variable part of the equation, that is repeated more than once in the equation. So here we can let a equals 3 to the x, and then we can rewrite the equation in terms of a, and then back substitute in terms of x. So we get 2a minus 5 is equal to 17 minus 8a. Remember, our goal is to make a simple exponential equation, and to be a simple exponential equation, we want a single base to one variable x equals the power. So we will collect all the like terms, so we'll have 10a on the left, and then 17 plus 5 will be 22 on the right. So we end up with a equals 22 over 10, which is the same as 11 over 5. And then we back substitute and we replace a with 3 to the x. So 3 to the x is equal to 11 over 5. And we know that 11 over 5 is not one of the perfect powers of 3 from the powers of 3 sequence. And so we don't even really consider trying to get a common base. We can immediately use logarithms. And so in this case, we can apply log base 3 to both the left and the right side of the equation. Or you can already be in the point of view where we rearrange this equation from exponential form, b to the x equals p, and we convert it immediately in one step to the logarithmic form. Keep in mind that the exponential form isolates the power, whereas the logarithmic form isolates the exponent. And since we are solving for the exponent, which is in the variable, which is x in the exponent, we want to use the logarithmic form. So if we simply just rearrange, we can say that we have a log base of 3, taken of the power now, because the power and the exponent will swap, and we have the exponent equal to x. So this is a good final answer, but it's not all that meaningful to us. In fact, we may want to use a change of base so that we could input this into our calculator carefully if we don't have a base 3 button on our calculator. Now we know that the change of base formula says we can make a ratio of 2 logarithms and we can use any base that we want. So base 3 is already used. We could try something else. Typically we use a base 10 or a base e. And it doesn't really matter which base we use because the answer is going to be the same. It just turns out to be easier if you use a base that your calculator has. So you could either use the natural log or the common log. And so I'm just going to work these 3 out on my calculator, which will do all 3 of these bases. In fact, it does all of these bases. So I'm going to type in log base 3 of 11 over 5 and get a decimal approximation, which is about 0.717. So what that really is saying is 3 raised to that exponent should give us about 11 over 5. So if I take that and multiply by 5, I get 11. In other words, 11 divided by 5 is 2.2, which is the same as 3 raised to that exponent. Okay, let's take a look at another way to do this. If I set up a fraction, then I can take the common log, log, of 11/5 divided by the common log of 3. And remember that's base 10. So if I approximate that, I again get 0.717, which is what I got when I used the logarithmic form directly with base 3. And lastly, I can do one more logarithm and set it up as a fraction. Oops. And in that fraction I'm going to put, not that, let's try this again, the natural logarithm of 11/5 divided by the natural logarithm, I think I can type it in directly, of 3. And so regardless of what base I use, I can get the same decimal approximation. In fact, I can use any base I like. I can even use the base of a fraction, such as 11/5, as long as the base in the top and the bottom are the same. And I will get 0.717685, etc., which is a decimal approximation. The exact answer for that, of course, is the answer that we found on the paper. Log base 3 of 11/5. Okay, I'll clone this page and we'll take a look at part B. So here in part B, we want to solve for x, and we notice that we have 2 terms involving x, but unlike in the first question where we had 3 to the x and an identical 3 to the x, here we don't have the same expression written twice. So the first thing we are going to do is rewrite the negative exponents and maybe clear the fraction. So for part B, I'm going to multiply both sides of the equation by 2, and that will help to clear the fraction. So 2 times on the left and 2 times on the right. So now we have e to the x minus e to the negative x is equal to 10. So then rewriting the negative exponent, we get 1 over e to the x. And I see again that I have a denominator. So I'm going to multiply all of the terms in the equation by the lowest common denominator, again to clear the fraction. This time I get e to the x times e to the x. So I'm just going to keep it written expanded for now. In the second term I get e to the x minus 1 over e to the x. The whole purpose of this red e to the x is to reduce or simplify or cancel the blue e to the x in the denominator. So I just get minus 1. Be really careful that you multiply all of the terms by the e to the x in red. And lastly we get 10 times e to the x. So we want to think about how to expand this, and we go back to our exponent laws. If we have x to the a times x to the b, we keep the base and we add the exponents. So that's exactly the same thing that's happening here. E to the x times e to the x, we're multiplying 2 powers and they have the same base. So when we're multiplying powers with the same base, we keep the base and add the exponents. And then of course x plus x is the same as 2x. So we can rewrite this expression here as e to the 2x. And then we have minus 1, and then we have equal to 10 e to the x. So this isn't really clear yet because we have e to the 2x, and we could have really seen this quantity as being something multiplied by itself, in other words something squared. So we could see this as e to the x all squared. To get rid of these brackets, we would have multiplied the exponents of x and 2, which does give us 2x. So it's consistent with what we did earlier. Now, if we have e to the 2x, that's the same as e to the x2. So you can swap the order of these exponents, and I could also see this as e to the 2 all to the x. So there's a few ways that we can play around with the exponent laws here. So I could rewrite this as e to the x2 minus 1 equals 10 e to the x, and then I can rewrite this as e to the x in brackets squared. So from seeing all of this exponent law gymnastics, we finally see a common term or a common factor, just like we did with 3 to the x in part A. So I'm going to let A equal e to the x, and then temporarily see what happens by substituting the a in. I get a squared minus 1 equals 10a. And so this is actually a quadratic equation in A, unlike the first part A of number 3, which led to a linear equation in A. And it was a linear equation in A because the exponent on A is 1. So in this case, I recognize that I have a quadratic equation, and I'm either going to factor or use the quadratic formula on this. Now, you might not be familiar with the variable being called a, so you could change it to something else. I just don't recommend that you change it to x, because that's something that was already used in the question. So a squared minus 10a, and I think it was minus 1, is equal to 0. So by the quadratic formula, a, which we normally write as x, equals negative the negative 10, plus or minus the square root of negative 10 quantity in brackets squared, minus 4 times the coefficient of the quadratic term, which is 1, and then multiplied by the constant term, which is negative 1. Now I'm purposely avoiding calling this quadratic formula in terms of negative b plus or minus the square root of b squared minus 4ac, and you'll notice I did it down here by accident, because we have an a here, which is the variable, and this coefficient of 1, we're typically calling that a from the standard form of a quadratic. So I'm avoiding using the letters a, b, and c because our variable is called a. So we end up getting a equals positive 10 plus or minus this discriminant, which is going to give me 100, and then negative times negative is positive, and 4 times 1 times 1 is 4. So plus or minus the square root of 104, or 104, all divided by 2. So I'm actually going to look at that 104 like this, and I'm going to see that I have 4 times 25 plus 4 times 1. And I can factor a 4 out of this, so I get 4 times 25 plus 1, which is still under the square root, 4 times 26. In other words, 104 is 4 times 26. And then I can make this the square root of 4 times the square root of 26. So from all of that, I can rewrite the radical as 2 times the square root of 26. And all of that is divided by 2. So from here, we want to simplify the quadratic solutions. So I'm going to divide 2 into the terms before and after the plus minus. So we get a is equal to 10 divided by 2, which is 5, plus or minus 2 root 26 divided by 2, which is just 1 root 26. In other words, we have that a, which was actually equal to e to the x, is either 5 minus root 26 or 5 plus root 26. So I'm just going to separate this as 2 different equations. And if we keep in mind that e to the x is a base raised to an exponent, we end up getting that e to the x is a power. And we know that powers must be positive. We can also say that 26 lies between two perfect squares of 25 and 36. And so the square root of 26 will lie between the square roots of 25 and 36. In other words, the square root of 26 lies somewhere between 5 and 6. In other words, the square root of 26 is 5 point something. And so, when we're taking a look at 5 minus root 26, or 5 plus root 26, we're going to get 5 plus a positive, so this number here is positive. And since e to the x is a base to an exponent, which is a power, and powers must be positive, this second equation is fine. However, over here, 5 minus 5 point something is actually going to be a negative number. And since e to the x is a base to an exponent, which is a power, and since powers must be positive, this is not an acceptable possible power. And so we have no solution coming from here. So we now have a simple exponential equation in the form of base raised to an exponent is equal to a power. It's just that that power is a little bit more complicated looking, and rather than replacing the square root of 26 with an approximate 5 point something, I'm going to leave it as the exact answer. So I'll just rewrite that equation. E to the x equals 5 plus the square root of 26, which is just a number, and our focus is here. We want to solve for x, so we can undo e to the by applying log base e to both sides. But another way of writing log base e, of course, is natural log, or ln. So we take the ln of both sides, and ln of e to the x cancel, because this is log base e of e to the x. So log base e of e to the leaves us with x. So on the left-hand side, after we apply ln to the left, we get just x, and on the right-hand side we have ln of 5 plus the square root of 26. So we could approximate that on a calculator, which will be whatever the ln of 10 point something works out to be. But as far as an exact answer is concerned, I'm happy with that one. So now let's take a look at equations that are posed as logarithmic equations. When we have a logarithmic equation, the input of a logarithm is a power. And powers, as we know, must be positive. So we have input restrictions or domain restrictions because we have the input of a logarithm is a power which has a restriction on it. So we have to be really careful when we're solving these equations. You could read these notes, but let's actually just take a look at some examples. However the original equation is posed, we need to consider what that power is. So your first step should be identify the power for the original equation. So in this case, the power is called x squared, and we know that powers must be positive. So to solve x squared greater than 0, there are a couple of ways we could do it. I might actually make the right-hand side of this inequality red, and then considering the graph of y equals x squared in blue, and the graph of y equal to 0 in red, we want the blue graph to be purely higher or greater than the red graph. So the blue graph is always higher than the red graph, except at the origin where the two graphs intersect. And that tells us then that x can be everything except for 0. So we would have a domain of this function of x is contained in the reals except for the single value of x equal to 0. So now we can forget about the domain and then just do some algebra to rearrange this equation to solve for the power. So since the variable is in the power, we want to switch from logarithmic form, which isolates the exponent, and we want to put that equation back into exponential form, which isolates for the power. So our power is what we're solving for because that's where the variable is. So we want to go from log form into exponential form here. Okay, so when we solve this and by putting it into exponential form, we see that we have a base of 3, we have a power of x squared, and we have an exponent of 4. And so we can simply use our first language approach, base to the exponent equals power. So this says that x squared is equal to 81. And when we solve this equation, we carefully take the square root of both sides. The square root of x squared is the absolute value of x, and the square root of 81 is only 9. But this, if we use the circle model, or we just know, we get two solutions. X either equals -9 or +9. We can look at the second equation, and we can apply some logarithm laws here, but the first thing we want to do before any logarithm law rearrangement is to identify the power. So in this case, the power is equal to x. And we know that powers must be positive, which is our domain condition or domain restriction number 3. So whatever values we get by solving algebraically, we must make sure that they satisfy x is greater than 0. So there's a couple of ways that we can solve this equation, and I'm just going to start off by rewriting the equation and giving our two different approaches. One approach would be to divide both sides of the equation by 2. So 2 log base 3, oops, I lost my x somewhere along the way. 2 log base 3 of x is equal to 4. And then if we divide both sides of the equation by 2, we will be putting this into a simple logarithmic form where we don't have any coefficient in front, we just have log base b of p. And so we end up getting log base 3 of x is equal to 2, and now we can exponentiate both sides of the equation. In other words, we can make both sides an exponent that we put on the base of 3. Now 3 to the and log base 3 cancel, leaving us with just x. And on the other side we get 3 squared, which is 9. Another approach we could have taken, instead of the 3 to the, we could have simply said, well, we have basic logarithmic form. So I'm simply going to rearrange base to the exponent equals power. So the base was 3, the power was x, and the exponent was 2. So I can say base to the exponent is equal to the power. And therefore x is equal to 9 is the same, whether we show the undoing step in slow motion or we get there directly. Just like when we had 5x equal to 15, we used to divide by 5 on both sides, but now we get there directly. That's the same as going directly here. Okay, so that's one of two methods that I wanted to show you. Another method, instead of dividing both sides of the equation by 2, would be to realize that we could use the logarithm laws. So we have 2 log base 3 of x equal to 4, and we could consider that coefficient of 2 comes up as an exponent on the x. And now we no longer have a coefficient in front of the logarithm, and we can go immediately to convert from log form to exponential form. So we have the base of 3 raised to the exponent of 4 is equal to the power of x squared. And so we have the same situation as we had over here. X squared equals 81, and we know that x is going to equal -9 or +9. Now, these two questions are slightly different simply because we had this exponent 2 not on the x but down in front. Method 1 showed only one solution for x, whereas method 2 shows two solutions for x. This is where we have to remember that we had a domain restriction not on some intermediate equation after rearranging using logarithm laws, but we had this domain restriction on the very original equation. And as a result, we must ensure that any answer we get for x satisfies the domain restriction. Well, we can immediately see that x equal to -9 does not satisfy the fact that x must be greater than 0. And so we say that this is an extraneous, an invalid solution. It's extra because of an additional step that the algebra introduced. It gave us this idea of getting x squared here, gave us two solutions, when really the x should only have had one solution here. And so our final answer, whether we use the red method or the blue method, is that x is only equal to 9. So unlike question A, where x had two solutions, because this says x can be anything as long as it's not 0, so both of these solutions are valid. In other words, x equals -9 or 9. But over here we have a different domain because of the fact that we started off not with an x squared here, but with that down in front. So the x squared power or the x power changes the domain. Okay, I can tend to take a long time with these questions because I want to give a lot of detail. Let's see if we can go through these a little bit faster. We have domain restriction number 3, and I'm just going to put 3 in a circle because we had denominators and radicands of even roots before. Domain restriction number 3 says that powers must be positive, and in this case the power is what we take the logarithm of. And so 2x plus 3 is the power, and therefore x must be greater than -3/2. So we'll just wait to see what answers show up algebraically and compare them against the domain. So I'm just going to write the word domain here because I didn't write it down already. So that's our domain, and now we're going to rearrange the simple log equation. It's simple because we have a single base, a single exponent, and a single power. And I'm just going to rewrite base to the exponent -1 equals the power 2x plus 3. So then we have 1/5 is equal to 2x plus 3, and we have a linear equation for x, so we can subtract 3 from both sides, and then we can divide both sides by 2. So 1/5 minus 3 is actually going to be 1/5 minus 15/5 if I multiply the top and the bottom of the fraction by 5. And so we end up getting negative 14 over 5. Now, instead of dividing both sides by 2, I'm going to multiply both sides of the equation by 1/2 because I had a fraction on the other side. And this ends up telling me that x is equal to, well, don't go straight away and multiply across because instead of 5 times 2, you want to reduce the 14 and the 2. 2 goes into 14 7 times, so we end up getting that x is equal to negative 7 over 5. So we sometimes get very excited, we have a value for x, we're done, we move on to the next question. But don't forget to go back and check against the domain. So where does negative 7/5 live on a number line? So on our number line, we know that x has to be greater than negative 3 over 2, which means to the right of negative 3 over 2. So you could use a calculator and get a decimal, but I'm just going to get a common denominator to compare negative 3 over 2 and negative 7 over 5. So my common denominator is 10, so I'm going to multiply the red fraction by 1 in the form of 2 over 2. And I'm going to multiply the blue fraction by 1 in the form of 5 over 5. And so the blue fraction is the same as negative 15 over 10. And the red fraction is the same as negative 14 over 10. And so negative 14 over 10 is actually closer to 0, and so negative 14 over 10, or indeed negative 7 over 5, lies to the right of this boundary x value. And so we want x to be to the right of that value, so this is an acceptable solution. It lies within the domain. For part B, I'll just clone the page and we'll try it again. I'll try the next page. The first thing we do before any algebra rearranging is to talk about the domain. And so we know that powers must be positive. So do not try to do any logarithm law combining, simplifying, or condensing before you state the domain. And indeed, I have an x here in red, and I have a power here called x cubed, which I will put in a different color. Let's call it green. And so I don't just need one power or the other, I need both powers to be positive. So x greater than 0 and, that's red x greater than 0, and green x cubed must be greater than 0. So we end up getting that x is greater than 0, and we also get from the green equation that this is the same as x being greater than 0. If you're not sure, you can take a look at this graphically. You can take a look at the graph of y equals x cubed, which is this cubic function, and we can intersect it with the line y equal to 0. And we want the green graph to be purely higher than the blue graph. Well, we see that those two graphs intersect at the origin, but we don't want the two color graphs to be the same height, and then the green graph is purely higher than the blue graph when x is to the right of 0. In other words, x is greater than 0. So we have for our domain here that x is greater than 0. And now we can do some algebra to rearrange and to simplify this equation. So 4 ln of x minus 3 equals ln of x cubed plus 2. Well, I'm going to take this exponent down in front as a coefficient and get 4 ln x. I'm going to add 3 to both sides of the equation so I can combine these like terms, and I notice that I'm going to get 3 ln of x plus 5. Well, if you wanted to, you could let the ln of x, which is a repeated quantity, be some other variable. Maybe I'll let it be w this time. And so I end up getting 4w is equal to 3w plus 5. In other words, 1w is equal to 5. And then we have to back substitute and replace w with the ln of x. And so when we do that, we end up getting a simple logarithmic equation. The ln of x is equal to 5. We have a single base, base e, single exponent, and a single power. So I can rearrange in one step from log form to exponential form. And I get that x is equal to e to the 5. Now I know that e is approximately 2.718, and so multiplying 5 copies of a positive number together is positive, which means that we satisfy the domain. Okay, Now we need to use the properties of logarithms to create a simple logarithmic equation. A simple logarithmic equation has a single base, a single power, and a single exponent written with a log form. Right now, this says that we've got one term on the left and one term on the right, and each of these terms represent exponents. So we're really talking about exponent plus exponent equals exponent, and so on. So to get this simplified logarithmic form, we need to condense and collapse some things here. So let's take a few things one step at a time. Of course, the very first thing we do is to consider any domain restrictions. Because we have the logarithm of stuff, the input of that logarithm, that stuff, is a power. And we know that powers must be positive. So before you try to do any condensing and solving, let's first of all think about the values that x must be. We have that 3x minus 2 must be greater than 0, and the next power, which is x minus 1, must be greater than 0, and the next power, which is e squared, must be greater than 0. But actually, e squared is a positive constant that's not a variable, so we don't need to write anything. And then the last power we need to consider is x, and x must be greater than 0. Now you might actually want to draw these as three separate colors on a number line, so that we can overlap and look for the intersection of the red, green, and blue. So from the red case, we end up getting that 3x is greater than 2 and x is greater than 2/3. And then we solve the second inequality for x, which says that x has to be greater than 1. And lastly, x must be greater than 0. So putting all of those three colored sets on one number line, we want to see where the values for x that are red, green, and blue all overlap. So the blue one I'll do first. X equal to 0 is here. We're not including 0, and we're going to the right. So that's a bit messy. That's our x equal to 0 set. Then x equal to 1 lies here, and all of a sudden we see that these two collapse into just x being greater than 1, because that's where blue and green overlap or intersect, which is what and means. And then 2/3 lies here, and so we want red and green and blue, and all of that just means that x must be greater than 1. So all of this simplifies to the set that x must be greater than 1. So now we can do something with the algebra, and that means we can use our logarithm properties to condense, collapse, and otherwise simplify this into a simple log form. Remember, a simple log form means a single base, a single power, and a single exponent. So here I'm adding two logarithms, which basically means I'm adding two exponents, which meant that we had to be multiplying the powers. So I get a single log base, and I multiply the two powers of 3x minus 2 and x minus 1. And on the other side, we might get a little bit confused here, but ln of e squared just means log base e of e squared. And every time you see log, you say, what is the exponent on this base to get that power? Or we could say that that exponent 2 can come down in front, and then log base e and e2 the cancel, and we end up with 2. So this exponent, this value here, is just 2, and then we have times the ln of x. And so from here, we can bring that exponent of 2 up, that coefficient of 2 as an exponent on the x. So we have the ln of some quadratic stuff. I can expand it to get 3x squared minus 3x minus 2x, which is minus 5x, and then plus 2. And all of that is equal to the ln of x squared. So now what we have is an exponent on the left and an exponent on the right, and they have the same base, which means by the one-to-one property that the two powers must be equal. And so I can come up with a statement that 3x squared minus 5x plus 2 must be equal to x squared. So this turns out to be a quadratic equation that we can solve either by factoring or the quadratic formula. This turns out to be a quadratic that we can factor, and we end up getting 2x minus 1 times x minus 2 is equal to 0. Then by the zero product property, either the first factor or the second factor must give us 0. So either 2x minus 1 equals 0 or x minus 2 equals 0. So either x equals 1/2 or x equals 2. Now keep in mind that we had a domain restriction, and we have to ensure that any values of x have to satisfy the domain restriction that x is greater than 1. Well, x is not greater than 1 here, and so we have only one solution. And our solution to this equation is going to be x equal to 2. Okay, take a look at the next question. In part B, we have a logarithmic equation, which means that the input is a power, and we have a domain restriction on powers. Powers must be positive. So before we do any algebra rearrangement using the properties of logarithms, we must state the domain. So we know that the first power of x plus 2 must be positive, and the second power of x minus 1 must be positive. So we get that x is greater than negative 2, and x is greater than 1. So if you wanted to color code those and put them on a number line, you can see where the red and the green sets overlap. So I'm just going to put my number line over here, and then x greater than negative 2 means that we're going from negative 2 to the right. X greater than 1 starts like this, and we're looking for where the red and the green intersect. And again, we have that the overlap or the intersection occurs for x greater than 1. So we have our domain, and now we're ready to do the algebra solving to convert this equation into a simple logarithmic form. In the last case, we didn't quite end up getting a simple logarithmic form. We ended up getting one logarithm with a base equals another logarithm with a base, and we were able to say that by the one-to-one property, these powers were equal. So either of these are the kind of forms that we're aiming for when we simplify using the properties of logarithms. So therefore, we can combine the left side. We have the sum of two logarithms. In other words, we're adding two exponents together, which means that we keep the log base and we multiply the powers. So again, we have x plus 2 times x minus 1 as the power that's joined by the two powers joined by multiplication. And on the right-hand side, this is just a number, and in fact, what is the exponent on base 10 to get the power 10? That answer is 1. So an approach here would be to take our simple logarithmic form and convert it into exponential form. Or we could, so if we did that, I'll just do it this way, we would get base 10 to the exponent 1 is equal to x plus 2 times x minus 1. Now you might have noticed that I had simplified log base 10 of 10 to 1. If I hadn't simplified it to that and left it as log of 10, I could merely have said that that power and that power are the same by the one-to-one property. And that's exactly what this red equation is telling me. There's another approach I could have taken, and instead of immediately switching to exponential form, I could have undone log base 10. In other words, I could raise both sides of the equation to a base of 10. And so that 1 can come in here, and all of this exponent can come in here. And I could ask myself, I have to use lots of brackets here, what 10 to the and log base 10 do? Well, they are inverse functions, so an f and an f inverse undo each other, and we end up getting that all of this is equal to 10 to the 1. Either way, we get this expression or this equation over and over and over again. So from here, we see that 10 is equal to x squared, I've got a typo here, this should be x minus 1. X squared times negative x plus 2x gives me plus x, and then minus 2. So I have a quadratic equation. I'm going to rearrange it into standard or function form, and then I'm going to recognize that I can actually factor that quadratic. Quadratics don't always factor, but in this case, this one does, and I end up getting that 0 is equal to x plus 4 multiplied by x minus 3. You can expand it to check and make sure we get the expanded quadratic here. Then, by the zero product property, if two or more factors multiply together to give 0, then one factor or the other factor must at least be 0. So we end up getting that either x equals negative 4 or x equals positive 3. But of course, we have to go back and we have to consider the domain, and we can only have values of x that are greater than 1, which is our second root. And the first root is extraneous because it does not live in the domain. In number 7, we are asked to solve the exponential equation 2 to the x plus 1 equals 3 to the x using several different approaches. I really like this question because there are lots of approaches and they all lead to the same answer. It looks pretty straightforward because we have a power on the left and a power on the right. But because the bases are not the same, we cannot set the exponents equal to each other by the one-to-one property. Furthermore, we know that this is an exponential equation because A, there's no logarithm written down, but B, the variable is in the exponent. So we want to undo what's being done to the variable. On the left, x is being added by 1 and then exponentiated base 2. So we would like to undo exponentiation base 2. However, there's another x in the equation and it is being exponentiated base 3. So undoing the base 2 exponentiation and undoing the base 3 exponentiation can form some of our methods. So for method 1, I'm going to apply log base 2. And we're going to apply that to both sides of the equation. So applying log base 2 to the left and the right, well, it works wonders on the left because it undoes 2 to the x, or sorry, 2 to the. So log base 2 and 2 to the cancel, leaving us with x plus 1. And then we still have log base 2 of 3 to the x on the right-hand side. Now we can use our property of logarithms to bring that exponent down in front. And since we have just thought about logarithms, it begs thinking about the domain again. We know that our variables are in the exponents, and we know that there are no restriction on exponents, and so exponents can be contained in the reals, which means that whatever we get when we solve, we don't have to compare and make sure satisfies the domain because, well, they will satisfy the domain by default. The domain is exponents can be anything. In other words, x can be anything. And so let's just continue solving, and we end up getting that x plus 1 is equal to x times log base 2 of 3. Now log base 2 of 3 means the exponent that we put on base 2 to get the power 3. We know that the exponent that we put on base 2 to get the power of 2 is equal to 1, and the exponent that we put on base 2 to get the power of 4 is equal to 2, so the log base 2 of 3, the exponent that we put on base 2 to get the power 3, must be an exponent that lies between 1 and 2. Okay, so the right-hand side just says x times 1 point something. So we're really just solving for x. I'm going to subtract x from both sides of the equation, and that will give me 1 equals x times log base 2 of 3 minus x. Now if I said 5x plus 6x and asked how many x's there are, we wouldn't say there are 2 x's. We would say there are 5 plus 6 number of x's. So we would factor the x out, let's put it at the back, and be left with 5 plus 6, which is 11 number of x's. So similarly, on the right-hand side of this equation, when I ask how many x's do we have, we wouldn't say we have 2 x's because x is written down twice. We would figure out what number is being multiplied by x. So we want to factor the x out. Keep in mind that there's an automatic 1 here. And when we factor the x out, we have log base 2 of 3, take away 1. And so this is the number of x's that we have, and so to solve for x, we now divide by that coefficient. So we get that x is equal to 1 divided by log base 2 of 3, take away 1. Now, this is a little bit messy, so I'm actually going to change both of those 1's into a logarithm with a base of 2. And so 1 is the same as log base 2 of 2. What is the exponent on 2 to get 2? It's equal to 1. And then I still had log base 2 of 3 here. Now my denominator is actually the difference of 2 exponents. So I'm going to keep the base and divide the powers, which is 3 divided by 2. And now I have an exponent divided by an exponent, which is a change of base formula, and I am going to absorb the base of 2, make the 3/2 the base, and keep the power of 2 at the top. Now that's one approach, but maybe I want to be a little bit more general. I liked that, but maybe I want to change the base to something a little bit more natural, in other words, base e. So I could just really rewrite that with any base that I want as long as the base is acceptable, and then I get the ln of 2 divided by the ln of 3/2. Okay, we'll leave that at that for now, and let's try method 2. Namely, apply log base 3 to undo the 3 to the. So we'll start off with the equation again, but this time we will apply log base 3 to both sides of the equation. So 2 to the x plus 1 is equal to 3 to the x, and put that equation in brackets and apply log base 3 to both sides. So we're going to have log base 3 of 2 to the x plus 1 on the left, and then log base 3 of 3 to the x on the right. So here I could say, what is the exponent on 3 that gives the power 3 to the exponent x? Well, what would I put in that box so that 3 to the box equals 3 to the x? I would put an x in that box. Or I could say that x can come down in front and be x times log base 3 of 3. Log base 3 of 3 is 1, 1 times x is x. Or I could simply remember my rationale for applying log base 3 in the first place, and that was to undo 3 to the. So the right-hand side is simply x. Now I can take this exponent of x plus 1 and I can bring it down as a coefficient of the logarithm on the left-hand side. And so then I can take this number log base 3 of 2 and multiply it through the brackets. So I get log base 3 of 2 times x. Now I'm just going to put that x not at the back because it almost looks like 2x is the power. But instead I'm going to put the x at the front and multiply by log base 3 of 2, and then multiply 1 and log base 3 of 2. Now I'm going to get my x's on the same side, so I'm actually going to subtract this term from both sides of the equation and get log base 3 of 2 is equal to x minus x times log base 3 of 2. From here, I'm going to ask how many x's do I have on the right-hand side. So I'm going to factor the x out and be left with a 1 minus log base 3 of 2. That's the number of x's that I have, so x is being multiplied by that number, and I divide both sides of the equation by the number in brackets. And then I can simplify the equation, the left-hand side expression, which I will put on the right, and simplify that by getting a log base 3 in each of the terms. So this one, I'm going to write it as log base 3, and not of 2, just because everybody else is, but in order to make it 1, the base and the power have to be the same. Then I can use my property of logarithms, which says I'm subtracting 2 exponents in the denominator. So I'm going to keep the log base, and I am going to divide the powers. So I get 3 over 2 here. And then I can go ahead and change the base to anything that I want, and in particular I might really like base e, so that I get the ln of 2 divided by the ln of 3/2. So if we look back to method 1, the ln of 2 divided by the ln of 3/2 is the same thing. So you might prefer method 1 or method 2. But I'm not done. In the end, we converted both of those answers for x to a log base e. So why don't we just apply ln to both sides in the first place? It's a neutral base rather than favoring base 2 or base 3. So if we have 2 to the x plus 1 equals 3 to the x, we can apply log base e. Even though it's not a base 2 or a base 3, it will still allow us to apply the logarithm property where the exponents can come down on the ground. And that's essentially what's making this equation difficult to solve, is that the exponents are up here in the air and we need them down on the ground. So the logarithm property, whether it's log base 2, 3, or e, means that these exponents can come down on the ground. And now we have x plus 1 multiplied by some number equals x multiplied by some other number. So that number ln 2 can multiply through the brackets, and we get x times the ln of 2 plus 1 times the ln of 2 is equal to x times the ln of 3. We want to get all of our variables on the same side, so I'm going to subtract x ln 2 so that we have all the variables on one side and all the x's on one side and all the numbers on the other side. Again, here we want to know how many x's we have, so I factor x out the back, and I have the ln of 3 take away the ln of 2. Now we could divide both sides by what's in the brackets, but I'm first going to recognize that I have an exponent, take away an exponent, and my logarithm property says to keep the base and divide the powers. So now x is being multiplied by a number, and that number is ln of 3 over 2. And so in the end, we see that x is equal to the ln of 2 divided by the ln of 3/2. And that is indeed what we saw in the previous cases. So think about which method that you prefer to use. Apply log base 2, apply log base 3, or apply log base e. However, I'm not done. I have method 4. And in method 4, I want to recognize something about the exponent laws themselves. If I have 2 to the x plus 1, this is the backwards of the exponent law says if I'm multiplying two powers with like bases, keep the base and add the exponents. Here I have a base and I have two exponents that have been added. So let's go backwards. In other words, let's expand this. This is going to be 2 to the x multiplied by 2 to the 1. So it's the reverse of the condensing exponent laws. In other words, we have 2 times 2 to the x is equal to 3 to the x. Now what makes this difficult to solve is that x shows up in two different terms. So I'm going to divide both sides of the equation by 2 to the x. But we have to be careful because we know that we can't divide by 0. Denominators cannot be 0. But we have, in this case, our denominator is 2 to the x. And we wonder, can 2 to the x ever equal to 0? Well, 2 is a base and x is an exponent, so this quantity is power. And we know that powers must be positive, and a positive number never equals 0. So 2 to the x indeed does not equal to 0, so we are allowed to divide by a positive quantity. So when we see this, now we're one step closer to solving for x because all of the x's are on the same side. And we have another property of exponents that says if I have a over b in brackets to the x, that the x can apply to the numerator and the denominator. And so we can go backwards and rewrite this right-hand side so that x shows up only one time. And this is the magic. This is when x can be solved because it only shows up one time in the equation. Now let me just rewrite this. We have a base raised to an exponent equal to a power. We have a simple exponential equation where the variable is in the unknown. So we can in one step rearrange from exponential form to log form. We have log base 3/2 of the power is equal to x. And so that's our final answer in a much shorter approach. The only thing we might want to do is make sure that we get the same answer that we had for all of the other ones, and we can apply the change of base formula. So I'm going to make this simple logarithm a quotient of two other logarithms, and my preferred log base every time was base e. So I can have log base e of something over log base e of something. And so the 2 goes as the top power, and the 3/2 goes as the bottom power, which indeed is the same answer that we got every other time. So this one method, or this one question with 4 different approaches, shows us how all of these logarithm laws are interrelated. In question 8, we are solving some exponential and logarithmic inequalities. In general, inequalities do not behave the same way as equalities, and so we should always think graphically to interpret the inequality solution while solving the associated equation using the algebra that we've seen. So what do I mean by that? Think of a red graph and a blue graph. So I'm making y equals 2 to the x the blue graph, and I have the red graph of y equal to 8. And we can see that this horizontal line intersects this one-to-one function at only one point. It should be easy for us to find the coordinates of the intersection, but if you're not sure, you're really taking a look at solving the associated equation 2 to the x equals 8. And here we can get that 8 is a perfect power of 2, and by the one-to-one property, x is equal to 3. So x is equal to 3, and on the red graph, which is a horizontal line, y equal to 8, we know that the y-coordinate is 8. So we're really particularly interested in the x-coordinate, and we see that there's one intersection point which creates one boundary line, and therefore two cuts of the x-axis. So we have region 1 and we have region 2. Now we want to figure out what set of x values in region 1 or 2 or on the boundary makes the blue graph higher, because this is really a y value. We're saying y equals 2 to the x, than the red graph, which is y equal to 8. And the blue graph is higher in region 2, so we're looking for our x values to not be equal to 3, because we didn't want an equal to according to the question, and going to the right. So our solution to this first inequality is x is greater than 3. Now, I know what you're thinking. You could have said, you made it really hard. I could have just applied log base 2 to both sides of the equation, and I would have gotten x is greater than 3. Yes, that's true for this one question, but it doesn't always work. If you were to apply that to the next question, it wouldn't necessarily work. And the reason is we have an exponential decay graph here. And as soon as the graph is not only increasing, but either turns around or decreases, solving algebraically for an inequality, it just doesn't work. So we want to find the associated pair of graphs. Here we're going to graph y equals 1/2 to the x. I'll make that a blue graph, which is the horizontal reflection of the 2 to the x graph, because 1/2 to the x is the same as 2 to the negative 1 to the x, which is 2 to the negative x. So we have a horizontal reflection of 2 to the x. And then I'm going to take a red horizontal line of y equal to 1/8. Now I know that height is at 1, so 1/8 is somewhere down around here. And I see that I have one intersection point, and I can solve 1/2 to the x equals 1/8. I can get a common base of 1/2, and by the one-to-one property I see that x is equal to 3. So that intersection point is at 3, 1/8, and I have a boundary here at x equal to 3. This creates region 1 or region 2, and I want to know where is the blue graph higher than the red graph, which is region 1. So in this particular case, my solution is going to be x is less than 3. So it's a little bit messy here, but I'll just put all that in a group, and I'll move it down, and from here I can interpret my solution as being x is less than 3. So if we had actually just tried to solve the inequality by using the one-to-one property, we would have said that 1/8 is 1/2 cubed, and then we would have said x is greater than 3, which is not the solution we're looking for. Now, you could come up with tricks, and you might be able to say, well, I have to write that as 2 to the negative 1 to the x, which is greater than 2 to the negative 1 cubed, and that would give me 2 to the negative x is greater than 2 to the negative 3, and now I can say negative x is greater than negative 3, and now I have to flip the inequality sign. But guess what? That flipping the inequality sign was just a trick to get you to get the right answer in the first place, because we didn't understand the graphical behavior. And how did you know that 1/2 as a base wouldn't work and 2 to the negative 1 would? It starts to become too much to memorize. We have to do some graphing anyway, and these are simple graphs to be able to make. So please think graphically when you're solving all inequalities, including this last one. So here we're going to have a blue graph, y equals log base 2 of x, and a red graph, y equal to 0. So I'm first going to graph y equals 2 to the x, which is our exponential function with a base of 2. And so y equals 2 to the x is this graph, and then log base 2 of x is the inverse graph, which we get by reflecting through the line y equals x. So this is my y equals log base 2 of x graph. Now I know the green graph had a y-intercept at 0, 1, and I know that my x and my y coordinates swap, so my blue graph has a point at 1, 0. Now I don't need any of that green information, it's just kind of getting in my way. I used it to come up with the blue graph. So now I have my blue graph, and the red graph is fairly straightforward. Y equal to 0 is just the x-axis. And I see that they have one intersection point, which is the x-intercept, which creates one boundary line and therefore cuts the x-axis into two regions, region 1 or region 2. And this inequality says I want the blue graph to be higher than the red graph, which occurs after the x-intercept, in other words, when x is greater than 1. So please just use the basic graphs for the exponential and the logarithmic curves, and then interpret which graph is higher than the other for which regions, and use that to state your solution. So there's a lot of details for exponential and logarithmic equations. Hopefully there's been enough review for you, and you can get more practice by looking at the textbook work or other worksheets on exponential and logarithmic equations.